Application of vectors, resultant force. Here's the situation. We've got some heavy object. Marina and Rosemary are moving the object by pulling ropes. It says Marina pulls the object with 20 pounds of force toward the east. Rosemary pulls with 10 pounds of force toward the north. Where is the object going to go, and what will be the total force applied on it? We can answer these questions by using vectors. Let me draw on this xy plane the vectors we're talking about. I'll start here at 0, 0, since that seems convenient. Marina's vector moves toward the east and has a length of 20 pounds of force. Rosemary is pulling in a different direction with about half as much force. She's pulling toward the north, it says, with 10 pounds of force. Maybe I'll call this vector vector M for Marina and this vector vector R for Rosemary. So where is this thing going to go that these two people are pulling on? Well, I can find the information I want by considering the resultant vector. In other words, the sum vector. Let's draw that on. I'll use the tip to tail rule. That means I'm going to have to move the Rosemary vector to the tip of where the first vector finished. Same vector, right? I can move them anywhere I want. The resultant vector goes from the very start to the very end. So here is the resultant vector. How about I use S for the sum of those two vectors? Vector M plus vector R equals vector S. That vector shows exactly what's going to happen to this object. It's not going to move toward Marina or toward Rosemary. It's going to move somewhere in between them. I think that should make sense to you. If you look at the picture, it looks like it's moving a little bit closer to Marina than to Rosemary. That's because she's pulling a little bit more forcefully. How about the total force? Well, the length of that green vector will answer that question. You say, well, won't it just be 30, 20 plus 10? If they were pulling in the same direction, sure, they'd be using 30 pounds of force, but they're pulling in two different directions, so they are slightly working against each other even as they're getting this object to move. Okay, well, how are we going to answer the questions? The first question is, in what direction is this object going to go? We can answer that by finding this angle. I'll call it theta, but if I can find this angle, then I can describe the direction that this object is going to move. This should not be too difficult because we've formed here a very simple right triangle. And I know two of the sides. I know this is 20, and I know this one right here is 10. So I can easily set up, since this is a right triangle, I can set up a tangent relationship. Tangent of that angle would be opposite over adjacent. That reduces to 1/2. This is an acute angle, and so to find theta, all I would have to do is use the inverse tangent button on the calculator. Tangent inverse 1/2 comes out 26.6 degrees. And I suppose the fancy way to give that answer would be 26.6 degrees north of east. Right? Marina was pulling to the east. The object, though, because Rosemary's pulling to the north, is going to end up traveling on a path that's about 26.6 degrees northward of due east. So we've answered the first question. How about the total force applied? Well, that's just going to be the length of that green vector, the length of vector S. How could I get that? Well, again, I'm in a right triangle. I can get that by simply using the Pythagorean theorem. 20 squared plus 10 squared must equal that length squared, that hypotenuse squared. That gives me 400 and 100, which is 500. All I need to do is take the square root of 500, and I've got my answer. So square root of 500 comes out about 22.4 pounds. And that's our answer. The net force being applied to this object is about 22.4 pounds. Now, one last question. What if I wanted to write down a component form for vector S? I actually wanted to have a name for vector S. Well, vector S is vector M plus vector R. I can see that vector M is the vector 20, 0, since it goes over 20 and not up or down. And I can see that vector R is the vector 0, 10. It doesn't go left or right, it only goes up 10. Well, that means my name for vector S is very easy. Just add the horizontal components, 20, and the vertical components, 0 plus 10 is 10. And so here is a component form of vector S. Let's look at a second example. This one's going to be a little trickier because I don't have a right angle in between my two vectors. So now I've got Luke and Morgan, and they are pulling ropes trying to move a donkey. The idea is that the donkey is right here, and they've got these two ropes attached. Luke is pulling with 80 pounds of force. Morgan is pulling with 50 pounds of force. And they're not pulling in quite the same direction. They're standing with an angle that's 20 degrees between them. The question says, how much force does the donkey need to exert so that it doesn't move? The idea is that the donkey is pulling back this direction somewhere, trying not to move. Luke and Morgan are pulling, trying to get it to move. Well, if the donkey is standing still, then whatever force it's using is equal to the net force provided by Luke and Morgan, so that once again I can answer this question by considering the resultant vector. Now, I find it easiest to take these situations and redraw them so that one of my vectors is along an axis. I just feel like that's kind of helpful. So I'm going to put that vector that's 80 units long, that's the Luke vector, so vector L. I'm going to put that one here along the positive x-axis. And then I've got this 20-degree angle here, and the other vector we'll call vector M for Morgan. So where's the resultant vector then? Well, I can do tip to tail rule. Let me copy the M vector down at this end. So there's another copy of vector M. And I know how tip to tail works. I start at the very beginning, I end at the very end. And so here then is the resultant vector. Okay? That's the direction of the force. If the donkey were to move, that's the direction it would move in. And the length of that vector tells me what I need to know. And that's all I need to know in this problem. By the way, the easy answer might have been to think, well, wouldn't I just add up 80 and 50 and the answer would be 130 pounds? And that would be true if Luke, Morgan, and the donkey were all standing in a straight line. If Luke and Morgan were pulling in the same direction, then sure, the total force would be 130 pounds. But they're losing a little bit of force since they're not standing in a straight line there. And you can see that the length of the green vector is a little bit shorter than the lengths of L and M combined. Let me call the green vector R for the resultant vector. I just need to know the length of vector R, and that will answer the question. Well, this is not a right triangle, which means I'm going to have to be thinking in terms of law of sines and law of cosines. Let's see, what do I know about this triangle? I know this length is 80. I know this length here is 50. I think I'm going to need at least one angle, and the only angle in this problem is 20 degrees. Now here's where you really have to draw a good picture and reason it out geometrically. Do you see when I moved vector M over to that second spot to do the tip to tail rule? I moved it exactly here. I have another 20-degree angle then in this picture. It's right here. It's got to be. The angle between the horizontal and vector M is 20 degrees. Well, that's huge because that means that I also know this angle. This angle that's in the triangle plus the 20 degrees makes a straight angle, makes 180. So that larger angle then must be 160 degrees. If your picture starts to get too messy, you may need to redraw some of these things with just the sides and the angles, just to make sure you're clear on what you have. I have 80, I have 50, I have 160 degrees. This is an SAS situation which means I can use the law of cosines to find that missing side, C, in this formula. If I find that side, I have the answer to my question. Well, let's go ahead and do that. I have, according to the law of cosines, C squared is 80 squared, 50 squared, 2 times 80 times 50 times the cosine of the angle in between, which we have discovered is 160 degrees. All I have to do to find C is square root each side. Now, I could clean up the pieces in there first if I want, but the calculator's not going to care. I really can just type that all in at once. So square root of 80 squared and 50 squared minus 2 times 80 times 50 times cosine of 160 degrees. And I am in degree mode, and I end up with 128.1. And that's my answer. The length of the resultant vector told me the information I needed. The net force that Luke and Morgan are using is 128.1 pounds. They're not losing that much compared to that 130 if they were pulling in a straight line. They're losing a little bit. If the donkey is not moving, then the donkey is pulling back in the opposite direction, also with 128.1 pounds of force. Thanks for watching.